Okay, this video is going to cover section 5.5, bases other than e. So in video 5.4, we talked about taking the derivative of an exponential function e to the x, which was simply e to the x. But what happens if we have an exponential function with a different base? So for instance, the derivative of a to the x, where a is a constant, anything but e. Actually, I'm going to skip these first two things. I'm going to change these notes around quite a bit, actually, today. So I want you to skip down to the very bottom here, and we're just going to learn what the derivative and integral of is of a to the x, where a is some constant. So if a is a constant, the derivative of a to the x is actually very similar to e to the x. So if we go back and think about the derivative of e to the x, remember it's simply e to the x. Well, there's something hidden that's actually going on here. You can see it with a to the x. So if a is a constant, and so I guess you could also say this would be e as well, this applies, then the derivative is going to be same as e to the x, it's going to be the exact same thing, a to the x, but then times the natural log of a. And if you apply that with e to the x, that would be times the natural log of e, and since e to the x is just e to the x, you can see natural log of e is just 1. So therefore, we just go e to the x. So with any other exponential function, we have to multiply by the natural log of that value. Now remember that natural log is natural log of a, the constant, is another constant. So a lot of times we do write it out front like this. And you might recognize this. We did this in the scavenger hunt with an example. I think it was take the derivative of 3 to the x. Maybe? Yeah, and I told you to take it by logarithmic differentiation because you have an exponent as x, and that totally works. You can do logarithmic differentiation, but now there's actually a rule for anytime you have a constant to an x. So that is just simply going to be, if I have 3 dx, that would simply just be natural log of 3 times 3 dx. It's that simple. Okay, so now if I want to take the integral of a to the x, remember the integral of e to the x is e to the x, but it's almost the exact same thing. Instead of multiplying by natural log of a, we're just simply going to divide by natural log of a, and then times a to the x, and then plus c. Okay, so again, I'm not going over a whole lot with this because same with section 5.3. With inverses, this is something that's not really very strongly tested on. So I'm showing you these. You might see an example. But I want to make sure that you see it. I'm also going to skip talking about change of base formula and taking the derivative of the log. This I've actually never ever seen. We typically strictly stay with natural log of x, so I'm not even going to talk about derivatives of the regular log. Okay, so we're going to skip to the second box here. So when can we use the power rule, x to the n? So now that we have exponential functions, a lot of people tend to use the power rule instead of the exponential rule. So if you have a variable base, okay, so that means x is your base, and then you have a constant exponent, so that is this example right here, then we can use the power rule. So what that means is bring down the exponent and then subtract 1. But you've got to be careful, though, with that, because what if you have a constant base with a variable exponent? You can't do that. You're going to have to use the rule we just learned or logarithmic differentiation. Same with, what if you have a variable base with a variable exponent, which looks like example number 1 here, then you also cannot use the power rule. So with both of these, you have to use logarithmic differentiation. Okay, and if you have a form, so the constant base with variable exponent, if you have a form of just simply a to the x, then that works out. What if you have a to the x plus 1 or something like that? So you can always use logarithmic differentiation. So that's another reason why I just kind of breezed over this example here, is because typically you can always use logarithmic differentiation if you forget the rule. All right, so we're going to do one more example. And that is if you have a variable base with a variable exponent. This doesn't have a rule that you can just apply, you just have to do logarithmic differentiation. So let's get some practice with that. So the reason why you want to do that is because you've got this here as as a function that's messing you up for a minute. So when I take the natural log of both sides, what happens is that 1 over x can now come down, and you get this here. All right, so now I haven't taken the derivative yet. I've just simply taken the natural log of both sides and brought down the 1 over x exponent. So now I'm going to take the derivative. So the derivative of natural log of y is y prime over y. And now over here we do have a product, and you can approach this as a product rule, or you can approach it as a quotient rule. It doesn't matter. I'm going to do product. So the derivative of, now remember we're taking derivative here. So the derivative of 1 over x, which is x to the negative 1, is negative 1 over x squared, times, keep the second the same, plus the first times the derivative of natural log of x plus 1, which is 1 over x plus 1. Okay, so now we're going to clean that up a little bit. So we have negative natural log of x plus 1 over x squared plus 1 over x squared plus x. And remember that over here you've got this y. So if I want to get y prime by itself, you're going to multiply this whole thing times y. Okay, but remember, since we know what y is in terms of x here, then we're going to have to plug this whole thing in for y. Alright, so I'm actually going to erase my y so I don't have to rewrite this whole thing, and just simply put my y here, which is x plus 1 to the 1 over x. Okay, so it looks really complicated, but I'm not going to try to clean that up. That looks fine to me. So that is another example of logarithmic differentiation.